Hello and welcome back to another Orange Coast College Mathematics video. In this video we're going to talk about solving systems of three equations. Similar to solving systems of two equations, we're going to use the addition method to solve systems of three equations. Now, what does it mean to solve a system of three equations? It means that I want to find an x value, a y value, and a z value such that all three of my equations are true at the same time. If we can find such values for x, y, and z, then that is a solution to our system. So, let's go over the steps for how we can actually solve these systems. First off, we're going to make sure that our equation is in standard form, as in ax plus by plus cz is equal to d, where a, b, c, and d are just constants, they're just numbers. Then we're going to use the addition method, and we're going to take a pair of equations and eliminate one of our variables. Usually you'll just eliminate x first, but you can eliminate any one that you want. Then we're going to take a different pair of equations and we're going to eliminate the same variable. So we'll be left with two equations without an x or without a y. Then once you've done that, we're going to have two equations that only have two of the variables, as in they'll both have y and z but not have x, or they'll both have x and y but not z. Once we have two equations with only two variables, that's like a system of two equations. And we can solve that either using the addition method or the substitution method. Once we solve our system of two equations, we will have found a value for one of those variables. Then we can solve that system of two equations, and then we can plug our solution back into any one of our three original equations to find the value of the third variable. Once we have that, we can check our answer by plugging our new solution into each of the original equations. If we get true statements for each of the three equations, then we know that it really is a solution. So let's try this with number one. So initially we have three equations, and each of them are already in standard form. They're all in the form of ax plus by plus cz is equal to d. So now I want to choose two equations and get rid of one of the variables. Now immediately I see that this middle equation has a coefficient of 1 on the x. So, if I'm going to eliminate the x's of the other equations, it might be nice to use that one, since all I have to do is multiply by whatever coefficient the other x has. So, I'm going to use this equation circled in black to get rid of the x's in both that top equation and that bottom equation. So let's focus on the top equation. So the top equation is 3x minus 7y plus z is equal to 2. And our black equation is x plus y minus 3z is equal to negative 4. Now, I want the x's to have opposite coefficients, so I'm going to multiply both sides by negative 3. Once I do that, I'm going to have 3x minus 7y plus z is equal to 2, and then negative 3x minus 3y plus 9z is equal to 12. From here, I can add these two together, and I'm going to have 0x, and we have negative 7y and negative 3y, so that'll be negative 10y, and then z plus 9z is 10z, and that's going to be equal to 14. So I've eliminated the x's from one of my equations. So now, let's try to get rid of the x's in the bottom equation, which I'm going to write in blue. So, I have 2x plus y minus z is equal to 1, and then I have x plus y minus 3z is equal to negative 4. Now again, I want the x's to have opposite coefficients, so I'm going to multiply by negative 2. This then becomes 2x plus y minus z is equal to 1, and negative 2x minus 2y plus 6z is equal to 8. Adding these together, we're going to have 2x minus 2x, so 0x, and we'll have y minus 2y, so we'll have negative y, and then we have negative z plus 6z, so plus 5z, and then 1 plus 8 is going to be 9. So now I have two equations that are in two variables. So I can make a system of two equations. this will be negative 10y plus 10z is equal to 14, and negative y plus 5z is equal to 9. Now from here you can use the substitution method or the addition method, whichever one you like. Personally, I like using the addition method, so I'm going to go ahead and turn this negative 1 on the y into a positive 10. So I'm going to multiply both sides by negative 10, and so we will have negative 10y plus 10z is equal to 14, and then positive 10y minus 50z is equal to negative 90. From here, I can add these together, and we're going to get rid of our y's, right? Negative 10y plus positive 10y is going to be 0y, but we've got 10z minus 50z, so this is going to be negative 40z equal to 14 minus 90 is going to be negative 76, and so we get z is equal to negative 76 divided by negative 40, but the negatives are going to cancel out, and so we get 76 over 40. Now, this isn't technically wrong, however, we can simplify this a little bit more. Now, I imagine the answer isn't immediately jumping out at you as to how this can simplify down, but one good trick is to notice that this is an even number divided by an even number. So they're both divisible by 2. So I can divide both of them by 2. So 76 divided by 2 is 38, and 40 divided by 2 is 20. Now again, 38 is an even number, and so is 20. So these are both divisible by 2. So 38 divided by 2 is 19, and 20 divided by 2 is 10. Now we can't simplify 19 over 10 anymore, so we know that z is equal to 19 over 10. Now that we know what z is equal to, we can plug it into one of our equations, and we can get a value for y. So let's go ahead and do that. Now, personally, I think the bottom equation looks a little bit easier since the numbers are smaller, so I'm going to use that one. So I have negative y plus 5 times z, but what is z? 19 tenths is equal to 9. Now I'm going to distribute, so we have negative y plus 19 over 2 is equal to 9. Now I want to get y by itself, so I'm going to subtract 19 halves over. So we have negative y is equal to 9 minus 19 halves. But we can rewrite this as 18 over 2 minus 19 halves. And so we're going to get negative y is equal to negative 1/2. But we get rid of our negative signs, and so we finally get y is equal to positive 1/2. Now that I know the values for y and z, I can take them and plug them back into any one of the 3 original equations that we started with. Now I'm going to use the one that I had circled in black because it had the smallest numbers. So we have x plus y minus 3z is equal to negative 4. Plugging in our y and z values, we have x plus 1/2 minus 3 times 19 over 10 is equal to negative 4. Now I'm going to go ahead and make all the constants have a 10 as a denominator. So we're going to have x plus 5 over 10 minus 57 over 10 equals negative 40 over 10. Combining like terms, we have x minus 52 over 10 is equal to negative 40 over 10. Now I can add 52 tenths over to the other side, and we're going to get x is equal to 12 tenths, but we can simplify that down to 6/5. And so we get a final answer of 6/5, 1/2, and 19 tenths. That is the solution to our system of 3 equations. Now, to make sure that this really is our answer, we should check it with each of the 3 of our equations. Let's check it with one of them for right now. Let's try the bottom equation. So let's plug our numbers in. So 2 times 6/5 plus 1/2 minus 19/10 is supposed to be equal to 1. So if we multiply this out, we get 12/5 plus 1/2 minus 19/10 is equal to 1. Now I'm going to make all the fractions on the left have a denominator of 10. So we're going to have 24 over 10 plus 5 over 10 minus 19 over 10 is equal to 1. Now if we add all this up, we're going to have 10 over 10 is equal to 1. That is a true statement because 10 over 10 is equal to 1. Now if we check it with the other two, we're going to see that we get 2 equals 2 and -4 equals -4, all of which are true statements. Since all of them are going to be true statements when we plug in our solution, it really is the solution to our system. And so we can move on to number 2. Moving on to number 2, we have a system of equations. However, this one actually looks different. While they are in standard form, it turns out some of the coefficients are actually 0. For example, in our first equation, we have x minus y is equal to 0. There isn't a z. While it may look like there's not actually a z, you can treat it as having a z, but with a 0 coefficient, so 0 times z. The same thing happens in the second equation. We have x minus z is equal to 5. There's not a y, but we can treat it as having a 0 coefficient on the y. So we're still dealing with 3 variables. Now for this problem, one of the special things about our 2 equations that are lacking a third variable is we actually get to substitute things in very quickly. If we manipulate our first equation, we have x minus y is equal to 0. Well, what is x equal to? X is equal to y. So anywhere I see a y, I can just replace that with x, effectively eliminating y. The same thing will occur for the second equation. We have x minus z is equal to 5. X minus z is equal to 5. Now I can rewrite z as z equals x minus 5. So anywhere I see a z, I can just plug in x minus 5. So in total, both of these equations allow me to eliminate my y's and my z's. So if I then take my third equation, we have x minus y plus z is equal to -1. I can replace my y with x, and I can replace my z with x minus 5. If I do that, I'm going to have one equation with one variable, as in I can figure out what the value of x is. So this becomes x minus x plus x minus 5 is equal to -1. This x minus x is going to cancel out, and we're just left with x minus 5 is equal to -1. I'm going to add the 5 over, and so we get x is equal to 4. So now that I have a value for x, I need to figure out what the values of y and z are. But luckily, we already have 2 equations that state what z and y are. Y is just equal to x. So if x is equal to 4, then we know that y is also equal to 4. Now z is equal to x minus 5, so z is equal to 4 minus 5, which is going to be -1. So we actually get a solution quite quickly of 4, 4, -1. Now it's best to check these. So we can plug it into the first equation. We have 4 minus 4 is equal to 0. And so we get 0 is equal to 0. That is a true statement. Now we can try our second equation, x minus z equals 5. So we have 4 minus -1 is equal to 5. And so we get 5 is equal to 5. That's also a true statement. And finally, we can check our last equation. We have x minus y plus z is equal to -1. So we have 4 minus 4 plus -1 is equal to -1. Well, the 4 minus 4 cancels out, and so we're left with -1 is equal to -1. That's also a true statement. So, since all 3 of these equations are satisfied at the same time, this really is a solution to our problem. So, 4, 4, -1 really is our answer. Moving on to number 3, I see that we have an equation right here. It has a coefficient of 1 on my x. So I think I'm going to use that one to try to eliminate the x's in the other equations. So I have x minus 3y plus z is equal to 4. Now I'm going to go ahead and do the second equation in red and the third equation in blue. Going with the second equation first, we have 5x minus 13y plus 13z is equal to 8. Now I want the x's to have opposite coefficients, so I'm going to multiply my top equation by negative 5. Once I do this, I'll have negative 5x plus 15y minus 5z is equal to negative 20. And we'll rewrite the red equation. 5x minus 13y plus 13z is equal to 8. Now I can add these together, and we're going to have 0x, 15y minus 13y is going to be 2y. Negative 5z plus 13z is going to leave us with 8z. And then negative 20 plus 8 is going to leave us with negative 12. Now we can move on to eliminate the x in our third equation. So we have x minus 3y plus z is equal to 4. And then in blue we have x minus 2y plus 5z is equal to negative 3. Now I want them to have opposite coefficients, so I'm going to multiply my equation in black by negative 1. And so we're going to have negative x plus 3y minus z is equal to negative 4. And then we have x minus 2y plus 5z is equal to negative 3. This is then going to become negative x plus x is 0x. And then we have 3y minus 2y, so we're going to have positive y. We have negative z plus 5z, so that's going to be 4z. And then we have negative 4 minus 3, so that's going to be negative 7. So now we have two equations in two variables. So we can solve that system of two equations. So let's rewrite it real quick. We have 2y plus 8z is equal to negative 12. And then we have y plus 4z is equal to negative 7. Now from here, I want to eliminate one of my variables, and I'm going to eliminate the y's because one of them has a coefficient of 1. So I'm going to multiply this by negative 2. And so what do we get? We get 2y plus 8z is equal to negative 12. And then we have negative 2y minus 8z is equal to positive 14. Adding these two together, we're going to have 2y minus 2y, so we're going to have 0y. And then we're going to have positive 8z minus 8z, so we're going to have 0z. And then we have negative 12 plus 14, so that's going to be equal to positive 2. 0 times y and 0 times z is just 0, so we end up with the statement 0 is equal to 2. Is this a true statement? No. 0 is not equal to 2, so something's wrong here. 0 is never going to be equal to 2, and it turns out that I can choose any value of y and any value of z, and it doesn't matter which ones I choose. I could choose a trillion and a billion, but because they're both multiplied by 0, I'm always going to end up with this equation of 0 equals 2, which we know is false. Since we know that's false and this is always going to happen no matter what my choices are of y and z, it turns out that there's actually no solution. There's no combination of y and z that I can make 0 equal 2. So there's no solution. Moving on to our last problem, I see again that our first equation has a 1 coefficient for x, so I'm going to go ahead and use that to eliminate the x's in the other equations. So I have x plus y plus z is equal to 7, and in red I'm going to do the second equation. So 3x minus 2y minus z is equal to 4. Now I want opposite coefficients, so I'm going to multiply my top equation by negative 3. This then becomes negative 3x minus 3y minus 3z is equal to negative 21. And then we'll rewrite the equation in red. We have 3x minus 2y minus z is equal to 4. Adding these together, we're going to have negative 3x plus 3x, so 0x. And then we'll have negative 3y minus 2y, so negative 5y. And then we have negative 3z minus z, so minus 4z. And then negative 21 plus 4, so negative 17. Now I'm going to use the first equation to get rid of the x in the third equation, which I'm underlining in blue. So we're going to have x plus y plus z is equal to 7. And then we have x plus 6y plus 5z is equal to 24. Now I want opposite coefficients, so I'm going to multiply my top equation by negative 1. And so we're going to have negative x minus y minus z is equal to negative 7. And then we'll rewrite our equation in blue. X plus 6y plus 5z is equal to 24. We can add these together and we get negative x plus x. That's going to be 0x. And then we'll have negative y plus 6y. That's going to be 5y. And then we have negative z plus 5z. So that's going to be 4z. And then we have negative 7 plus 24. So that's going to be positive 17. And now we have two equations in two variables, so we can try to solve that. So let's rewrite it. We have negative 5y minus 4z is equal to negative 17. And we have positive 5y plus 4z is equal to positive 17. Adding that together, we're going to have negative 5y plus 5y, so 0y. And then negative 4z plus 4z, that's going to be 0z. And then we have negative 17 plus 17, so equal to 0. Well, 0 times y is 0, and 0 times z is also 0. So we end up getting 0 is equal to 0. Is that a true statement? Well, yeah, right? 0 is equal to itself. So what's going on? Well, back up here, we have 0 times y plus 0 times z. Does it matter what I choose for y and z? I could choose 10 for y and 1,000,000,000 for z. It's going to be 10 times 0, which is 0, plus 1,000,000,000 times 0, which is 0. And so the left side is always going to be equal to 0. It doesn't matter what I choose for y and z. I could choose 5 and 10. I could choose 100 and 2,000. I could choose 1,000,000,000 and 1,000,000,000,000. There's multiple answers that I can plug in for y and z such that I'm going to get this true statement of 0 equals 0. It turns out there's actually going to be infinitely many ways that I can plug in y and z. So there's actually infinite solutions. Let's take a closer look at our system of two equations up here. What do we actually see? Every single one of our pieces had opposite coefficients. As in, if I multiplied this top equation by negative 1, I would get 5y plus 4z is equal to positive 17, which would be the same thing as our bottom equation. So it turns out this system of two equations was actually just two copies of the same equation. Since they were the same thing, that's why we got infinite solutions. While saying that there are infinite solutions is correct, it's nice to know what solutions they are. There's probably some rule that they follow, and it's going to have to deal with our system of equations. So just like how we would write our answer to a system of two solutions that has infinite solutions as a line, we're going to do the same thing with a system of three equations. First off, we want to get an equation for z in terms of another variable. Now, we have this equation right here. 5y plus 4z is equal to 17. We can turn that into an equation that says z is equal to stuff. So let's do that. Let's rewrite our equation. So 5y plus 4z is equal to 17. So let's go ahead and solve for z. So I want z completely by itself, so I'm going to subtract 5y over. So we're going to have 4z is equal to negative 5y plus 17, and now I'm going to divide everything by 4. So we get z is equal to negative 5/4 y plus 17 over 4. So now I can take this z and plug it into one of my original equations. I'm going to choose the first one because it was the easiest. So we have x plus y plus z is equal to 7. So now I'm going to plug z in. So we have x plus y plus negative 5/4 y plus 17 over 4 is equal to 7. I'm going to go ahead and multiply everything by 4 just to get rid of our 4's in the denominator. So we're going to have 4x plus 4y minus 5y plus 17 is equal to 28. So now, combining our y terms and subtracting 17 to the other side, we have 4x minus y is equal to 11. So I'm going to add y to the other side, and I'm going to subtract 11 to the other. So we're going to get y is equal to 4x minus 11. So now I have an equation for y in terms of x, and I have an equation of z in terms of y. So if I just pick an x value, I can then figure out my y value. And then, because I know my y value, I can figure out my z value by plugging it in. But instead of going through that whole step, I can actually write z in terms of x by plugging in my new equation in here. So let's go ahead and find z in terms of x. So z is equal to negative 5/4 y, but what is y equal to? Y is 4x minus 11 plus 17 over 4. This becomes negative 5x plus 55 over 4 plus 17 over 4. Combining like terms, we have negative 5x plus 72 over 4, which then becomes negative 5x plus 18. So we now have an equation for z in terms of x and an equation for y in terms of x. So I can finally write my answer. My answer is x, 4x minus 11, and then negative 5x plus 18. From here, I can figure out any point that I want. All I have to do is plug in an x value. Once I do that, I have my x coordinate, and then I plug that x coordinate into both here and here, and we get my y coordinate and z coordinate. From here, we can actually plug this solution into any one of our equations, and we'll see that we get a true statement. So, for example, we have x plus y plus z is equal to 7. So let's go ahead and plug in our answer in here. So x is just x, y is 4x minus 11, and z is negative 5x plus 18. And all of that is going to be equal to 7. So let's go ahead and combine terms. So we have x plus 4x minus 5x. Well, that's going to be 5x minus 5x. So we're going to have 0x. And then we have negative 11 plus 18. Well, negative 11 plus 18 is going to be positive 7. And so we get 7 is equal to 7. It's a true statement. If we do that with the other equations, we'll see that we get the same thing. So this really is the answer to our system of equations. One thing that's nice to note, though, is that if we look at all the x's, right, we have x and 4x and minus 5x. Since this adds up to 0x, it doesn't actually matter what x value I choose. I'm still going to get a true statement. So there's multiple x values that I can actually throw in there, and I'm still going to get 7 equals 7. In fact, there's infinitely many x values that I can throw in there. So that further supports the idea that there are infinite solutions to this system of equations. That's going to do it for this video, and I hope to see you in the next one.